5-1, we made it. We're doing this thing. Let's get into it. We are solving systems of equations by graphing. If you need a refresher on graphing, here you go. Most of these equations are going to be in y equals mx plus b form, where b, well, what do you think b is? B is our y-intercept. That's a lovely point that we can plot out usually first. M is our slope, which we sometimes call the rise or the run, especially if it's a fraction. We're substituting the given points into both equations to determine which ordered pair satisfies the system of linear equations. We're continuing to graph both equations and label the point of intersection to verify the solution. So the point of intersection, that's a new term, which is, again, as mentioned here, it's pretty much called a solution. So where they intersect, that means that it's a solution. So let's make a note of that. A solution is a point of intersection between two or more lines graphed out. But we'll also see an algebraic interpretation of this for the first one. So there we go. The algebraic interpretation, I'll show that first for this one. So this is claiming, or pretty much asking or inquiring if 0, -2 is a solution. So we could try that with the first equation. We'll plug in where x is 0. And hopefully the whole outcome is going to be -2. And we'll see if that's going to work or not. 3 times 0 is 0. 0 minus 2 is -2. -2 equals -2. That's true. Okay, so that's okay for the first part, but let's try it over here for this second equation. And I'll even switch up the color for this. So if I was checking this point with y equals x, we soon see that it's going to claim -2 equals 0, which is false. And isn't that kind of conflicting? Because here we said it worked for the first equation, but not the second. So we would say that this is not a solution. It worked for one equation, but not for the both. So it's just a point that's on one of the lines, but not both. So that's a big deal there. Is that okay? Does that sound okay with you? Let's try 2, 2. Well, let's try the second equation first. So if we were trying 2, 2, this is claiming that y is 2, x is 2, 2 definitely equals 2, so that's a true statement. We were trying that for the first equation. Again, we're focusing now on 2, 2. So we would get 2 equals 3, parentheses 2 minus 2. 3 times 2 is 6. 6 minus 2 should be equal to 2, but I don't know. Does 2 equal 4? Doesn't. So this is false. So this is also not a solution. If you eventually do the same thing we did, plug in for x, see if the end statement's true, you're going to see that 1, 1 is our solution. Does that make sense? Eventually you get both equations saying that the outcome's true, so that's why 1, 1 is our solution. And well, you know what? Pause the video, take a moment, take this all in. We're gonna start graphing in just a second. So take a moment, pause this, copy down what you need, and we'll move ahead in a second. All right, we're here. We've been graphing these for quite a bit, so I'm just gonna hop straight in. I'm gonna use this color for this line, and I'll switch up the color for the other one. So this has a y-intercept of -2, and our slope is 3, so I can go over 1, up 3. And this point here is actually going to be pretty important, because didn't we say that was something already? Yeah, we said it was going to be important. So we'll see that in just a second. Try to make this as straight as possible. There we go. For the other line, that was just y equals x. So I'm going to switch up my color on this. I'm going to make this blue. Y equals x has a y-intercept of 0. but we can go up 1 over 1 to get the next point. Again, although it's not written, our slope here is 1. So we can treat that as 1 over 1. Going up 1 over 1, and keep doing that quite a bit. Eventually to get this line in formation. We see our blue line cutting through. And then lo and behold, we said that 1, 1 was going to be a solution for us. It still is. And it is right here. Right there. That's 1, 1. That's our solution. That's where the two lines intersect. Does that make sense? Can I answer anything else? Draw some arrows to show that it keeps going. Why not? We got the time. Take a moment, and you're going to be trying out this next problem seen over here. Try 2. Go for it. Pause it. Try it. See what works. You should have gotten something to the effect of 2, 7 being your solution for both equations. If you plug it in, it makes a true statement that 7 equals 7. Again, that would work for both if you simplify those correctly. If you graph these out, you get lines that look like this. You get a solution at 2, 7 as we expected. If you need some points for the first equation, I'll help you out there. Your y-intercept was 0, 3. You were then going up 2 in the y direction and up 1 in the x direction. We've seen problems like this with this pattern of adding 2 for y, adding 1 for x. So that would be for this equation here. Hope that helps. 3 and 4 are similar. You're just graphing those out. So there's no points that you need to plug in there to see if they're solutions or not. That's an important thing to notice. For problem 5, take a moment, read through it. We're going to touch base in just a second. Maybe practice what we did in 5-1. Think, what's the story without numbers? What's the story with numbers? And then see if you can tie together everything. I wrote out what this looks like without numbers, but I'll talk about the whole story. We have a theater wants to take in at least $2,000 for the matinee. Children's tickets cost $5. So I've already read through this once. I talked about it without numbers. You can find that here. Children's tickets cost $5. Adult tickets cost $10. The theater can seat up to 350 people. 5 combinations of children and adult tickets. That will make the $2,000 goal. All right, well, we honestly have a bunch of ways we could do this. We could try, well, let's think. We know that if I call X the number of children's tickets, and if I add on Y for the adult tickets, I know that this should be less than or equal to 350. And I know that if I was going to aim for my goal, I know that if X is the number of children's tickets that are purchased, and if I add on the number of adult tickets, but multiply that with 10, this is going to talk about the money now. And we're trying to get this to be greater than or equal to 2,000. All right. So you have a few options with how you can get this started. I mean, we need this to be less than or equal to 350. So let's just go crazy. Let's say that we want 350 adult tickets. Oh, we'll know it. Yeah, let's back that up again. Let's do 349 adult tickets. And we'll just have one pipsqueak child ticket, which would satisfy the 350. And then if we were aiming to get how much money that's going to bring in, I think this part's pretty simple. We've seen this already in the Desmos activity. We know that we would have 5 times that 1, and we would add on 349 times that 10, which is going to get us how much? How much do you think? That would help us pull in $3,495, which is more than the 2,000. So this combination here works. So lo and behold, we have one option that works. And there are tons of answers we could have gotten. I know that in this problem, I was kind of hinting towards using X and Y. Again, X is the number of children's tickets purchased. Y is the number of adult tickets purchased. So if you want to go like that, you could say that the child ticket was 1, adult ticket was 349. That's an option that works. See if you can find another. Some other options, again, there are a bunch that you could have come up with. You could have also done something like 2 children, 348 adults. That could work. You could also do 3 and then 347. Again, you want to fill the seats. So as long as, I mean, if you want everybody to do this thing and get into the theater, in my eyes, make it 350 people going. So of course, you don't want to overshoot that, so just play it smart. I guess not too many children are going to see this movie. Maybe it's a Saw movie. I don't know. Those options could work. All right, and we're graphing a little bit more to round out the go. Hope that's okay with you. You've done a great job so far sticking with us. This has us graphing each equation below, determining if 3, 5 is a solution to the single equation, and then finding 2 points other than 3, 5 that are solutions to the equation. Show the points on the graph. Sure thing. Let's hop right into it. I'm going to take care of 9 first. Hope that's okay with you. This one is a fraction for the slope, which is okay, but I figured it'd be nice to see that variety where our rise is going to be 1, run is going to be 2, our y-intercept is 2. Sorry, rise is 1, run is 3, y-intercept is 2. We're moving over 3 units and then up 1 to get another point here. I'll fill in a little table also so you can see what points that we mapped out. We got 0, 2, we got 3, 3. Let's map out another one, go up 1 over 3. This is 6, 4. And then do you happen to see a pattern here with these numbers? Hopefully you do. They're adding 3, whereas the y term's adding 1. We've done this before. So just keep running it. 9, then 5, 12, then 6. All of those are good. The point that they were asking us to clarify on, I think, was 3, 5. So we see pretty clearly that 3, 5 is not going to work. And I'll even show on the graph why that's not happening. So we want to hit all these points. Again, your line should be straight. Maybe use your ID, use a textbook, use something that's a straight edge so that your line looks nice and neat. As we were looking before, 3, 5 should have been on here, but 3, 5 is way up here. And since it's not on the line, it's not a solution. And so I think that's what all the Go problems are about. You're plotting these lines, seeing if 3, 5 is a solution. And I want to say that's it. Well, we'll look at these real quick. Hold on. Yeah, let's take a pit stop. Problem 12. The tables below represent different arithmetic sequences. Again, arithmetic means we're adding or subtracting to get to our next number. We see that here we're adding from the first term to the second term to the third term to the fourth term. So we're adding different intervals once, twice, 3 times to go from 17 to -7. So the way we could do this, we can measure these distances or the difference. So I know that I'm starting at 17 and then I keep going until I hit 7. So this is going to tell me that I've moved a total of 24 blocks. And this was over the span of 3 hops, but we do this over 3 times. So this is saying that for every move, we're deducting 8. So let's try this. 17 minus 8 is going to go in here. So 17 minus 8 is going to get us 9. 9 minus 8 is going to give us 1. 1 minus 8 gets us -7. So that's good. For the equation, we've seen these before. We've put together equations that are explicit. Think of this as like a day 1 problem where we have y. We're taking our difference of -8. Well, let's actually back it up. What term are we starting with on day 1? We're starting at 17. We're then deducting 8, x minus 1 times. Or if you want to rearrange this, -8, x minus 1 plus 17. And that makes sense because every time we move forward in our term, we're deducting 8. So that's what our equation here would be. Hope that this video was helpful. If you got any questions, holler, let me know. Thanks for watching.